Hey ladies and gents, today we are going to do something really cool with this energy and heat thing in the unit that we've been working on in AP Chem. Today we're going to do a little bit with thermite. So before we start doing any of this, we need to go look at some stuff over there. All right guys, for the notes portion of this video, you're going to really want to utilize the pause function, try some stuff yourself, and then check and make sure that you're okay. So the first pause that I would say is to activate after I tell you to balance this equation right there. Go ahead and pause it, try to balance it yourself, and then continue on. Okay, you should have gotten 2, 1, 1, 2. Okay, now that you've balanced it, we're going to look at this delta H of formation to find the delta H of the reaction for the above reaction. So you got to use the chart in the back of your book. Look for the delta H of formation of aluminum, of iron oxide, of aluminum oxide, and of aluminum itself. And then what we're going to do is we're just going to fill it in here and then see what it calculates out to be. Okay, so go ahead and pause the video, look up those different ones. Remember, it is or how we arrange this in here. And that's all the hint I'm going to give you. Let's see if you match me. Okay, you should have found 0 for the pure element in terms of kilojoule per mole. You might have looked at the kcal number instead, but that's okay. It's a quick conversion. You would have also found for this side of the reaction, 822.2 kilojoule per mole. Then over here, you would have found negative 166.9.8 kilojoule per mole. And then, of course, since it's an element, you'd find 0 kilojoule per mole. So I bet you're wondering what you have to do with these coefficients. Yes, you do need to multiply both of those zeros by 2, but in the end, does that really matter? No. So when you pull it all together, you get negative 847.6 kilojoule per mole. The only reason I'm adding in this multiply by 2 value, even though it is insignificant for this question, is because it is still significant for other questions. You need to remember to multiply this value that you find in the back of the book by its coefficient. All right. So continuing on, I want you to now draw this potential energy versus reaction coordinate diagram, and don't forget to include some of those things that we've been talking about inside of class. So go ahead, pause the video, draw that, and then check and see if you're good. All right, you should have drawn something like this, where we have a higher ledge for the 2 aluminum and the iron oxide, a lower ledge for the Al2O3 and the 2 irons, and you should have remembered to include an activation energy before it gets down to here. So this is, of course, the reaction coordinate zone down here. And then this right here we label as that delta H double dagger. That's just the activation energy. I'm not asking you to calculate that. All I'm asking you to do is say that the difference between these two heights is going to be that delta H value that you just discovered or found up there through calculation, which is going to be negative 847.6 kilojoule per mole. Okay. And now the question's on this page. However, the work is on the next page. So, you're going to look at the specific heat capacity as the amount of energy needed to change the temperature of 1 gram of a substance 1 degree Celsius. So like for water, it's 4.18 joule per gram degree Celsius. For mercury, it's 0.14 joule per gram degree Celsius. So that means that we could, heat up mercury or utilize the same amount of heat energy to heat mercury up a lot higher, 30 times as much as water, for instance. So water has a much higher specific heat capacity than mercury. Okay, some background to what we're actually going to do. So the heat capacity of iron is 0.45 joule per gram degree Celsius, and for aluminum oxide is 1.25 joule per gram degree Celsius. So what I want you to do is, with those mole values from the balanced equation, I want you to calculate how many joules per degree C I can raise. Now, remember, you're going to be using the balanced chemical equation, you're going to be using the specific heat, and you're going to be using the mass. Wait a minute. Okay, so what equation is this? Oh, this is that Q equals mc delta T thing. Nah, Q equals mc, because we've got to figure out moles, not delta T. We're going to figure out the change in temperature. So it's just Q equals mc because we're looking at heat capacity here. All right, give it a try, pause the video, do some calculations, and then see if you're right. So you should have looked at 1 mole of aluminum oxide here and 2 moles of iron here. You should have multiplied it by its molecular weight of 101.96 gram per mole and 55.85 grams per mole. And then you multiply it by that specific heat. For this one, it's 1.25 joule per gram degree Celsius. For this one, it's 0.45 joule per gram degree Celsius. And you're going to get 127.5 joules per gram degree Celsius here and 50.3 joule per degree Celsius here. This is not per gram degree Celsius, it's just per degree Celsius. And what's the ending of this? Besides, okay, yay, these are our answers. This is in 1 mole of Al2O3. And this is in 2 moles of iron. So if we look at this, this is asking you to sum these for the reaction. So why did we look at 2 moles of iron and 1 mole of aluminum oxide? Because that's what we had in the balanced chemical equation. So if you add those two up, you get the 177.8 joules of energy to raise the temperature in our product 1 degree Celsius. Cool. All right. Now that you know all this in the reaction, we can actually look at how many joules are inside of everything. And we are going to look at, we got it from over here, we got 847.6 kilojoules, so really that's 847,600 joules. And then with this one, our heat capacity, we're just going to pull down from here, that's 177.8 joule per degree C. So I want you to tell me what the temperature change is going to be of this. Use these two values, tell me a temperature change. All right, pause the video, do the math. All right, you should have used 847,600 joules. You should have multiplied it by the inverse, 1 over the 177.8 joules, so that our unit conversion gets us in degrees Celsius to get 4,780.7 degrees C, or with sig figs, 4,800 degrees C. So we're going to change this temperature by 4,800 degrees C. That's the temperature that we're going to produce by putting 2 moles of iron and 1 mole of aluminum oxide together. Well, if you look up the melting point of iron, you'd find that it is 1,538 degrees C. So what are we going to see when we look at this thing go? We are going to see molten iron form. Okay, so ladies and gents, let's go mix some stuff together, and then let's go outside and see a thermite reaction take place. Okay, now that we have the notes done, now that you understand a little bit about the process of what's happening, let's mix some stuff up and get ready to go outside. We're not doing thermite inside. That's very unsafe. But we are going to look at how much of the two things we need. Inside of those notes over there, we saw from the balanced chemical equation, we need 2 parts of aluminum to 1 part of iron oxide. So up here, I have some aluminum, and I also have some iron oxide. I've got some spare just in case I don't have enough, but I'm going to tear the scale down to 0. And 2 parts of aluminum is 53.96 grams, Okay, that's way too much. So what we're looking for is 54 grams. There we go, 54 grams. Boom. And we need 1 part of iron oxide. Iron oxide is this Fe2O3. We need 159.7 grams of this. And we're going to do 100 in this cup. In this cup, and then we're going to do 59.7 in the other cup. There we go, 159.7, give or take. All right. So the next thing that we have to do is mix the two together. I'm going to put one of the iron oxides in, then one of the aluminums, and then the other iron oxide. And then I have this stir bar right here, which I'm going to integrate the powder particles, because if I don't do this, then it just won't do anything. So we want as many of those aluminum particles touching as many of those iron oxide particles as possible while this is going on. I still see quite a bit of red at the bottom there, so I'm trying to dig down, dig deep, to get that stuff from the bottom. All right. And now, this is ready for outside. Well, to get fully ready for outside, we're going to use our assistant over here, and we're going to take a walk, because we're going to put this mixture right here on this cart. And what's also on this cart is a ring stand, a butane torch and a lighter, and then some sand. Well, what we also have to put on that cart is this clay pot right here, because that is going to fit right in there. So the next time you see this setup, the clay pot will already be up there. I'm going to use a little bit of this paper towel right here over on the cart to plug the hole that is right there inside that clay pot. And then I need this, magnesium, because even though I have that butane torch right there, I am going to make myself a magnesium wick that will stick out of that clay pot so that I can light it safely before we rock and roll on this experiment. Okay? So the next time you see me, I'll probably be wearing a Stormy Chromer, and we'll be outside. See you in a little bit. Yep. Okay guys, here we go. I've got that set up over there. I've got a camera over there, and I've got Mr. Lewis over there on live stream. And all I'm going to do now is I am going to take this burner, I'm going to light it, I'm going to light that, and then I'm going to run like heck. Okay? You want to get me lighting this, Mr. Lewis? Okay. All right. And all right, we're going to get a little bit closer here. And what you see now is that is molten iron. So we have taken the oxidation away by mixing it with aluminum and iron oxide. And that temperature right there is the one that we calculated inside. And I'm going to have to let this sit here probably, well, based on the temperature, probably until about 2 o'clock. The smell out here is insane. It smells really bad because we just created a micro foundry at the Math and Science Center. So I hope you enjoyed that, and I'll see you in class.